Hey, welcome everyone. Sorry about the technical difficulties at the start. I hope you're all excited as we are for this month's Serverless London Meetup. We've got two great talks today. First from Xav about calculating the real cost of your serverless application, and another one from Gunnar where he'll talk about chaos engineering for Azure. Sorry if you can hear the view in the background, we're fixing that right now. Anyway, before we get started, I just want to thank Theodo and Senzo for sponsoring the event and making this possible. First up, Xavier's going to take it away with his talk.
All good? Okay, let's go. Let me show. Cool. Hi everyone, thanks for having me today. It's a pleasure to participate in this meetup from a distance, from Paris. That's at least the opportunity of 2020, is that we can share much more easily talks between each other around the world. So today I want to talk about how cheap is serverless, which is like one key topic regarding the technology. Before that, I'm gonna talk a little bit about myself. I'm Xavier Lefèvre. I'm VP of Engineering at Theodo France, based in Paris. So Theodo is a tech product consulting and development agency. So we build apps and the best as possible for clients, for different types of companies and industries. And I'm mainly focused on expanding our serverless practice in the company for the benefit of our clients, because we do believe that it brings a lot to the table. And my Twitter, if you want to follow me, I do tweet about serverless. So what brings us here? Serverless benefits. So when we talk about serverless benefits, we can mention those like auto-scalable in and out. It could be ecological. If you have sources that show and that prove that it's ecological, I would love to. It's super. It would be super nice to know. But theoretically, it's supposed to be ecological. There is some improved dev and ops lead time, security as well, because when you don't have security experts, you enjoy the expertise of your cloud provider. And you're supposed to have cheaper infrastructure when you pay only what you use. Then it really depends on your use case, of course. But if we take a look at all that can translate into money at the end. What's not auto-scalable needs to be handled manually by people that have to be paid, or at least that have to spend time on those topics. Improve dev and ops lead time means we take longer to do something. Security means you need to have the expert. So at the end of the day or of the month, everything translates into being more cost efficient as a company. So, and all of that is included in one bill. All of those different aspects are somehow included in one bill. So you have all your AWS services here, and they all encompass these different aspects. So how do you understand that? What does it mean? It means there's a topic called a notion called TCO, which is total cost of ownership. That's helpful to understand and to assess this global idea. And it includes three aspects: the development costs, so really of starting and building a project with developers, infrastructure cost of running this project and those apps, and maintenance costs about taking care, maintaining those infrastructures and the code that's going to live for some time. And when you assess the value or how cheap serverless can be, you need to assess it on this global scale, because it helps to really understand the value of serverless. As said before, when you take a look at the bill, it encompasses a little bit of all of that. So, but it's not that clear. But the question is it really cheaper? That's something I've been wondering myself and asking myself for quite some time since I started entering in the serverless world. Is it cheaper for for which use cases is it cheaper? It was complicated for me to really trust this fact. There is sources, so there's several sources, theoretical ones. You have a good article from Yan Kui that explains this TCO topic, this TCO notion. You have other sources that are more return of experiences, more specific about real use cases, and there are always as well some calculators. Either some very advanced ones like AWS one, which is anyhow way too complicated if you don't know what you're gonna do, or some that are too basic that compare Lambda against EC2, for instance. But when you think about serverless, or when you don't know serverless but you want to know if it's cheaper for your use case, I thought it was missing something in there. So with some of my colleagues, we started to build a calculator to help with that. How is it different, this calculator? That's a question. What did we build to make a difference from what already exists? And the idea behind is that it has an opinion on what a serverless architecture is. You may have seen this diagram on Twitter pass a few months ago because it made a little buzz, not positive and negative. It was a crazy discussion, but it was interesting because it was pointing out some concrete and difficult topics about the fact that this is too complicated, but it's also a different way of seeing architecture when you represent a serverless architecture. So this calculator has an opinion. It thinks that those services like API Gateway, Lambda, DynamoDB that you need to use in a fully serverless architecture. It goes a little bit further than that. When you think about the way of calculating costs for each of those services, there's a lot of variables. We're going to see it a little bit when we're going to enter the calculator. So we decided, based on our experience, based on what we see from different clients or from the community, we decided to preset some of those variables in this way, thanks to this opinion. So let's take a look at this calculator. Let me try to put it bigger. It's going to be better anyhow. Okay, and how do I remove this bar if I don't make it? Yeah, I think. All right, that seems better. Cool. So that's what it looks like. It's a spreadsheet for the moment. So the idea is going to be to expand it eventually, but for the moment it's a spreadsheet. It's easier to iterate, and it's accessible. I released it, and you can use it afterwards if you want. I'm going to give you the link. How does it work? So on the left side, you have some variables. We still had to display some basic variables to let you adapt this calculator to your use case. But the idea is to make it as simple as possible. So there on the top left, if you don't have any idea, or if you don't have precise data of your use case you want to try, you can just select predefined scenarios. So for instance, e-commerce with low traffic. What's low traffic? It's 50 sessions per day. So let's say that we have a medium traffic for a blog. Here we have 2,000 sessions per day, and all the variables are being automatically updated. On the right, you can see that according to our calculator, and we battle tested it, you're going to pay around $20 per month for a fully serverless architecture. So fully serverless, as I explained before, and as is written here, it's auto-scalable by design because we selected all serverless services from AWS. It's serverless, so it's up-to-date, distributed, asynchronous, and secured. There is user and auth management with Cognito. There is data and file storage with DynamoDB and S3. There is real-time updates with API Gateway WebSockets. There is monitoring with CloudWatch, and there is some workflow management with step functions. So everything is in there. And it's supposed, with 2,000 sessions per day, to cost you $20 per month, which is quite cool. And then there is more advanced variables: number of sessions per user per month, percentage of authenticated users, which is going to have an impact on Cognito, for instance, of course, etc., etc. So those are the user variables. And then below, you have the architecture variables, which we decided to display still, because we thought that it depends. It's still some variables that depend on people, and that there are no clear consensus in the community. And your feedback are welcome. So you can change those, but you need to know a little bit about serverless to be able to do that. But if you don't know about serverless, you can trust those and change these if you have a little bit more advanced data, and still see the output, which is gonna have a meaning. And if you want to if you want to change it, there is dedicated columns which we call custom to be able to do that. So let's say that it was the same basis. No, it's 10% and 30% because I was in e-commerce. Okay, so the only difference now is the number of sessions per day. So if I have 3,000 sessions per day, and in my e-commerce has much more authenticated user, maybe they're all authenticated because they have to. It's a private sale, and you have to be authenticated to have access to the products. So you're gonna say 100%, and then on the right side you're gonna see that it's still $0 because I think we're still under the free tier. So if I put, let's now yeah. Okay, so now we have 30,000 sessions per day for still a number of 5 sessions per user. And there we see that Cognito starts to be a little bit more expensive. What's under the hood? We created 1 tab per service. And you have the full calculation, the source and the full calculation here. You can see that what's grayish, more gray, is what we set in the constants. A little bit more gray is what we set in the stone, and what's white is what can be updated from the front, from the main dashboard. For the moment, we have four different types of applications: e-commerce, collaboration tool. So collaboration tool, by that we mean that it's like a tool you use internally, and many collaborators are going to update it in both ways. So it happens quite a lot. A blog and a chat. And then the traffic can be from medium to very high. So high is going to be 40,000 sessions per day, and very high is, no, it's not in order. And very high is going to be a million sessions per day, which is super high, which is cool. Here it starts to be expensive, of course. Next, let me go back to my slides. So now, thanks to this calculator, we can assess and understand a little bit more about costs of different types of applications in an easier way. What happens with the low traffic example? So if we take an e-commerce with 50 sessions per day, it should cost around $1.6 per month. A blog site is going to be $0.5 per month. So it's quite accessible, but the traffic is quite low. What's funny is that I compared it with the smallest EC2 VM, which is supposed to be cheap. And I found out that the smallest EC2 VM is going to be $3.43. So a serverless application of this size is going to be, and which is going to be much more complex than just a simple EC2 VM that comes naked, is going to be much more powerful and cheaper. So here the champion is quite clear. Serverless takes the win. And then if we go a little bit higher on traffic and we go for medium, so 2,000 sessions per day, here it gets closer. Serverless e-commerce is $70 per month, and the serverless blog would be $20. I took a corresponding EC2 VM based on experience, and let's say the M6G large, but once again, it's one VM. So there is no database behind, there is nothing, you have to do it by yourself. And so it's never going to be enough. This VM is going to be $62 per month. So still here, as for light traffic, the prices get closer, but the added value, everything that comes pre-boosted with e-commerce makes it take the win. So that's quite clear for medium traffic. Then if we go further for high and very high traffic, high traffic for 40K sessions per day and very high for 1 million sessions per day. So I put everything together there because the costs are higher for sure. So it's going to be for the high traffic, 1.7K per dollar per month for e-commerce and 475 for a blog. And then very high traffic, which is insane, is going to be 49K for the e-commerce and 12K for the blog. So the problem is that those figures are more complex to compare. You cannot compare it to a VM. And here, those systems are much more complex anyhow. Those companies that have those systems, when they're not with serverless, they have many components, have microservices, have different types of software running behind, and teams as well. There is a lot of things happening. So how do you compare it? How do you know that this is worth it? And I should invest in serverless as a big company. So here we come back to the TCO, the total cost of ownership. So there are several sources talking about that, some serious white papers, and most of them talk about the fact that you can give to AWS many generic ops tasks, and that either you refocus ops on more customer and business-centric tasks or elsewhere, which means that you can reroute or save money. If you consider that for a high traffic classical app, we have two ops. Let's say that for the sake of the exercise, only one remains in serverless. From a white paper from Deloitte, they said that those generic tasks, you could divide by 8 how much time you're supposed to spend on those tasks. So I kind of stayed conservative by dividing by 2. It's not that simple for sure. There is still a lot of requirement for ops that's different. Serverless changes a little bit the game, but that's clear that you can reuse this time and this cost for more better purposed tasks. So if we take this example, it would mean that we can save or reroute $12K per month because we reduced by 1 divided by 2 the size of the ops team, which is this calculation is made based on an average employee cost in Paris for a company. So just taking this figure, when you compare this figure with the $1.7K you give to AWS on the traffic, it was on the high traffic example above, it starts to get quite interesting. So now, what's to come with this calculator? I shared it with an article and got some feedback. I'm starting to work on those feedback from the community. So for instance, I saw that Joe Emison sent this tweet this week, and he shared his bill, and it was quite nice because I was capable of as well comparing from something from the outside that the calculator was not far, and his bill is quite cheap for what he has. He has 50K sessions per day, and it costs $734 per month. And I tried quickly with the calculator with a basic set of parameters, and I was around 1,200, something like that. So I was above for sure, which is better above than below. But it was not that far. And so the next step for me is going to be to improve on those feedback, to go get them. So I'm going to have a discussion with Joe to understand a little bit more about why it's this cost, what's his architecture, where does it save money that I didn't see in the calculator, to refine the outputs. And potentially, then after refining the calculator, building an open source app out of it to make it more clearer and available to everyone. So thank you. I think I talked quite fast. The calculator presentation and article and the sources of all my research is on the Medium blog. I can send you the presentation after. The calculator itself is there, and my Twitter is still the same. It's this one.
Cool. Thank you so much, Xavier. That was a lovely talk. We've got one question so far. It says, could you put the calculator of serverless costs on the description of the video? Yes, we can. And I had a few questions listening to your talk. I know we work with different clients at Theodore. I was wondering, how many times have you actually got to use the calculator so far?
I got to use it 2 times with 2 clients in Paris, and you got to use it a little bit as well in London, I think. Just more on more specific aspects. I think you are more around calculating lambda and lambda at edge. No, in Paris, I used it 2 times. It was interesting. The one time was for a client that we built a full serverless application for them from the ground. And as it's from the ground, it's greenfield. We're not completely fully in production with as many users that they will have in the future. So they wanted to understand a bit where they're heading. So I used it with my client, which is technical as well, and we built it together, the variables, to adapt it to the constraints of his project, and then he could see what it would cost him. So it was interesting. He was happy to have that. It was more to really anticipate what it would cost him rather than comparing, because he was not capable of comparing anyhow. And then for another client right now, we did the same, but to reassure them this time, to show them that they had some figures about what they have and they want to change to serverless. And we used it to show them that it's not going to be out of proportion if you have the right the right architecture, the right skills, and the right FinOps skills as well. You can always optimize those costs. So that's the 2 times I used it for work at Theodore.
Amazing. And do the clients are they very convinced by it? The tool looked very impressive. I was wondering how less technical people, if they trust the number that comes out.
It's the first one was completely, but maybe didn't ask enough questions. Could be just that he trusts me. But no, he was convinced. He really liked it. He was even eager to try it with me. Like 6 months ago, I talked with him that I was building a calculator, and he said, "I just want to know right now how it works. Can you give it to me?" But it was not yet ready. So no, he's completely trustful about him. He was. The second client are still assessing. There's a lot to process, and we are building serverless fully serverless architecture with them. So they have a lot to process, and they go from something quite old to brand new serverless architecture. So it's going to take a little bit more time than a calculator.
Yeah, I think that's very similar to one last question we've got from the chat. They asked, have any clients refused to use serverless architecture because they've been afraid of new technology?
It happened once, indeed. Indeed, it happened once. It's rare, but one time I think it was more in the way we communicated it. I think we showed an architecture diagram as this one. Let me go back, something like that, and from the feedback of the client at the end, there was several stuff that ticked him off a little bit, and one of those was, it's too complicated. You propose something too advanced for our need, for our use case, and we didn't see it coming. So it was a good learning for that. But it's the only one. The rest, for the moment, no, they didn't say it's too advanced, it's too fresh for us. Never. The vendor lock-in is more of a problem usually.
Yeah, no, one is not that bad. That's pretty good. I was expecting more, to be honest. Anyway, thank you again, Xav. That was a lovely talk. Next up, we've got Gunnar, who's talking about chaos engineering with Azure. I'm very interested to see AWS Serverless Hero talk about Azure, so that should be a good one.
Bye-bye.
All right. Hey, everyone. Great to be with you. And yeah, AWS Serverless Hero talking about Azure. That's going to be interesting, right? So let me share my screen. There we go. And I hope you're able to see it now. Okay. So chaos engineering for serverless in Azure. That's the topic of the night. And this is the abstract of the talk, that principles of chaos engineering have been battle tested for years using traditional infrastructure like containerized microservices and virtual machines and so on. But the question is, how do the principles work with serverless functions and fully managed services? So this is our agenda. We'll start off by talking about what chaos engineering is. So this is not about serverless in particular. Look at some of the motivations behind why we want to do chaos engineering. Then we'll look at how to perform chaos experiments, some of the challenges we see with serverless today, and how chaos engineering can help us. Look at some of the common weaknesses that we see in serverless applications today. And of course, we're going to finish it off by doing a few chaos engineering experiments in an Azure environment. So just short about me. I am an evangelist in Sweden, working at a company called Opsio. I have about 20 years of experience in the IT industry now. Started off with development. I am involved in both the AWS and the serverless community in the Nordics by organizing user groups, conferences, and so on. Yeah, I've been named an AWS serverless hero. Very proud of that. And I have 3 kids, which is more or less what got me into chaos engineering, I guess. So let's jump into it. What is chaos engineering? Well, first off, chaos engineering is not about breaking things. We often hear that breaking things on purpose is what we do. And I think that's great marketing lingo, but it draws attention to the practice. But breaking things isn't the purpose. Sure, we do break things now and then using chaos engineering, but the breaking part isn't the purpose. Learning is the purpose with chaos engineering. And we often hear that chaos engineering should be used in production. And hearing this can be an obstacle for anyone trying to introduce chaos engineering in their organization. We want to do it as close to production as possible. So you can do chaos experiments in test environments, in dev, staging, playground environments, and so on. But the more production-like the environment is, the better, of course. So you can think about replaying traffic, using it with load testing and so on to get it more production-like. And there are a bunch of major companies doing chaos engineering that aren't doing it in production today. And also, chaos engineering is not only for big streaming companies. There's a reason why Netflix is used as a reference over and over again for chaos engineering. They have a head start since they started what is chaos engineering today. And there's also a big company with brand recognition, so it's easy to use them as an example. But you should remember that you don't have to be Netflix to do chaos engineering. You don't even have to be like Netflix. Data is showing that more and more companies are doing chaos engineering. Companies are hiring chaos engineers, SREs, that are responsible for chaos experiments. And today it's used by companies ranging from small startups to big e-commerce companies or banking institutions. So chaos engineering is more and more widely adopted today. So this is a line from the website principlesofchaos.org, and we can't really have a presentation without showing this. So chaos engineering is the discipline of experimenting on a system in order to build confidence in the system's capability to withstand turbulent conditions in production. And when we read this, we see that it's less about doing things that are chaotic and more about experimenting. And so the chaos part of chaos engineering, it's actually more about what we have already inherent in our systems. So let's break that down a bit. So chaos engineering is about performing controlled experiments to inject failure. And doing experiments, it makes it sound quite scientific, and it really is scientific. We create a controlled experiment and we measure the result of that experiment. And it's common to compare it to a vaccine, which these days, of course, resonates in that we inject failure into a system, and the purpose is to make the system stronger in the end. And chaos engineering is about finding the weaknesses in a system, fixing those weaknesses before they break. So no matter how much we focus on making our systems resilient to failure, there are always unknown factors that come into play. We have different traffic patterns. We have third-party dependencies, network issues, code deploys, and so on. So by doing our experiments and measuring the results of those, we can find these weak points in the system and draw them out. And finding these and fixing them can help us avoid these big outages that we just don't want to have. And chaos engineering is also about building confidence in your system and in your organization. So when we do these experiments and we find weaknesses, we can build confidence in how the system works and how the system is supposed to work. But we also build confidence in the organization. So building a resilient system means that we need to have people that are able to operate that resilient system. And by building confidence in the organization, we gain trust in both the organization, the people, and in the system. So when we perform experiments, we will learn new things about our application. So let's look at some of the motivations behind why we want to do chaos engineering. Nines don't matter if users aren't happy. That's a famous quote by Charity Majors of Honeycomb. And I think we can have these dashboards full of SLAs, SLOs, SLIs, and whatnot, measuring all types of metrics from our systems. But what actually matters in the end is having users that are happy, users that are happy that the system works as they intend. So, are your customers getting the experience they should? Everyone who builds or runs a system has customers, be it internal customers or external customers. And we often say that nothing is free on the internet. So no matter if you run an e-commerce site, an ad-driven blog site, or a SaaS solution, downtime or issues probably costs you money. So that can be in decreased sales or just by users leaving your platform and stop using it. So what happens when the incident is there? Are you confident that your monitoring and alerting will actually notice? Will the on-call get that page needed to start engaging with the incident? And you probably have your runbooks or playbooks describing how to act when incidents or outages occur, but is the organization ready to handle outages? You probably do fire drills for in case of fire in your building, but do you do fire drills for incidents? And every time there is an incident, we have a huge opportunity to learn about the conditions that exist for the incident to take place. So are you learning from the incidents you have? And that brings us to, for me, the greatest motivation behind chaos engineering, and that is, don't ask what happens if a system fails, but ask what happens when it fails. A resilient system isn't one that does not fail, but one that maintains an acceptable level of service in the face of failure. What happens when the system fails? Well, chaos engineering helps us reveal that. So now we've looked at what chaos engineering is and why we want to do it. So now let's look at how to run chaos experiments. And we'll do that by following some quite simple steps. First off, we're going to define what's called the steady state. We're going to form what's called an hypothesis. We're going to plan the experiment and then run it, measure and learn from the experiment, and then we can scale up or abort and fix it. So let's dive into each of those. Defining the steady state. And the steady state is what's the normal behavior of a system over time. So it's highs and lows, it's ups and downs, and so on. And we find this steady state by using system metrics and business metrics. And the business metrics, they are usually more useful for us in defining the steady state. The system metrics, they might be in a non-serverless system, it might be the number of instances, it might be CPU levels, and so on. But business metrics, they are perhaps instead number of active users, number of purchases, searches, and so on. And those metrics, they are usually closer to that happy user. And it's important to remember that the steady state that we define, it's not necessarily continuous. It might differ over time. So Black Friday is probably way different from a normal day of the week any other time of the year. So with our steady state in place, we need to form what's called an hypothesis. And to find and build our hypothesis, we use what ifs. So we ask questions. What if the primary database goes down? What if there is latency in the system? What if my function throws an error code? And by asking these questions, we try to form an hypothesis around that. And when creating the hypothesis, we can actually inject failure into any layer of the stack. So it can be on the application layer, it can be on the infrastructure layer, networking layer, and so on, even at the human level. So what if Bob isn't in the office today? And to form the hypothesis, we're using, once again, a scientific method, if-then. If the primary database goes down, then we will move to the fallback database. If there is latency in the system, then we will still be able to maintain a good enough service for our users. And when we're creating these hypotheses, it's quite common to find problems, find known problems already before we actually do an experiment. So if we find that this hypothesis ends up in a problem, well, then we just fix those problems before we go ahead with this hypothesis and experiment. Then on to actually planning the experiment based on the hypothesis we created. So we gather a lot of smart people in a room, people who are involved in that part of the system, and we try to whiteboard the experiment in detail. So looking at the hypothesis I said before, if the primary database goes down, we'll move to the fallback. Well, then we look at how can we simulate this? How can we create this experiment, remove the primary database from our system? But we always, when we create our experiments, we try to make it as small as possible early on. So our first experiment should always be with the smallest possible blast radius, as we call it. And a blast radius, that's basically how big of an impact can this experiment have if it causes a failure. So we can limit it to a certain number of users, specific countries. We can limit it by single Lambda function, for instance, instead of doing something that might cause an outage. And we need to make sure that we notify the organization what we're going to do. No one wants to be the person creating an experiment that causes a failure and no one knows about why things are going down, be it in production or in test or staging and so on. And when we create our experiments, we need to have a way to abort. So have this stop button ready. If we remove the primary database, well, you better make sure to have a way to get it online fast. If either the experiment actually causes an outage, or just when you've seen that it worked, you've proven your hypothesis. All right, so now we've created our experiment and we've run it. Now it's time to actually look at the result from the experiment. So we use the metrics we set up earlier when we set the steady state, and now we want to prove or disprove the hypothesis. If the primary database goes down, we move to the fallback database. Well, that's a fairly simple hypothesis, and we can then look at the metrics. Was that what happened? Did we move to the fallback? Were people still able to use our solution in the way it was intended? So the question is, was the system resilient to the injected failure? Yes, it moved to the fallback database and things went along smoothly. A great question is, did anything unexpected happen? And unexpected things might be both positive and negative. Negative outcome might be that, for instance, that we didn't move to the fallback database, or we weren't able to even remove the primary database. But unexpected things might also be that we find new sources of reliability or robustness in our system. Well, we tried to disable the primary database, but it actually, in an instance-based solution, spun up new instances before we were able to take the other ones down. That perhaps might be unexpected for us. So we find new ways for the system to be resilient to failure. And when we've done our experiments, once again, it's important to notify the organization, share what you've done and what happened from it, so that others understand why you do this and why it is important to continue doing it. Next step then is to decide what's next. So we use the learnings from our experiment to improve. We can improve both the system and improve the way the organization handles the failures perhaps that was caused. We get bug reports, we create action items and so on based on the findings from our experiment. And with the confidence we've gained with a successful experiment, we can scale up. So if we were limited to a certain country before, we can add additional countries. If we only added latency on 10% of invocations, we can increase to 20%, for instance. So increase that blast radius that we set earlier. And when we increase the blast radius and have a bigger scope, we usually find new effects. For instance, latency, that's something that if we inject it on a small percentage of invocations, for instance, it might not affect the solutions. But as we increase that rate and have it in 20, 30, 40%, then perhaps we're getting a latency that is affecting a bigger part of the system. So it might reveal new effects that we didn't see before. All right, so now we've seen how to run our chaos experiments, and it is pretty straightforward, and it's not that chaotic. So this brings us to the serverless part of this. And I want to look at some of the challenges we see with serverless. So this is the Microsoft definition of serverless. This is an Azure talk, right? So serverless computing enables developers to build applications faster by eliminating the need for them to manage infrastructure. And that's great. We don't want to manage infrastructure. We just want to focus on the business logic. That's great. But as we know, there are still servers in serverless. That's what everyone keeps saying to us. And there is, we just don't manage them. And that leads us to some of the challenges with serverless as well. So we don't have any servers to manage, which is good, but it also means that we have potential sources of failure that we don't or can't control. So many of the underlying failure modes, or the failure modes for the underlying infrastructure, is unknown for us. We don't know exactly what can happen. And we have less heavy lifting, and I'm all for less infrastructure work. We just have to remember that every time someone sets up or configures infrastructure of some sort, they usually learn a lot about how it works and what some of the failure modes are. They learn and find sources of failure and are aware of those. Once again, a lot of things in serverless are unknown for us. And beside Azure Functions as perhaps the most common part of our architectures, we have a vast amount of services to choose from when building applications. Every one of those services have their own potential sources of failure, and many of them have these unknown failure modes as well. So for each function and for each service we use in our serverless application, we have separate configuration, we have We have separate security policies and so on. And this is all great for control, but it also gives us the opportunity to introduce failure. Failure in deployments, in configuration, and so on, just by having so much control of each small part of the system. And usually our architectures are more granular. We saw the example in the talk earlier of a basic service architecture. And when we get down to the granular parts of it, it can become quite complex. And serverless in itself, it is a distributed system by default, just the way serverless works. And more complexity, well, that means more inherent chaos in our system. All right, so then let's look at what can we do in regards to chaos engineering for serverless. And creating chaos experiments for traditional infrastructure, that can be fairly easy. We can shut down instances, we can destroy pods, we can cripple network traffic and so on, because we have control over the underlying infrastructure. But when we design chaos experiments for serverless, we need to think about it in different ways. So we have to be a bit creative here. So when we create them, we can start off by looking at some of the common serverless weaknesses we see in our architectures. So are we handling errors correctly in our application? No matter if we handle it inside our code or we use features in the service from the cloud provider, we better make sure that we handle errors correctly. So releases from the cloud providers where they take load off the error handling is great, but I want to make sure that to test that, and we can do that by using chaos experiments. With the functions we use and dependencies in other, in this case, Azure services or third parties, we want to get our timeout values right. So in many cases, they are correct, at least when in the steady state. But what happens to our timeout values if there are issues, for instance, latency? And with event-driven architectures becoming more and more common, how we handle our events is key to having a resilient and reliable system. So are we queuing events correctly? What happens to events in case of service failures? And when we use many services and many third-party dependencies, we often trust that these services are there. But what happens if they aren't there? Are we using fallbacks, graceful degradation, and so on in our applications to handle those types of failures? And of course, we have failovers as well. I don't want to jinx us, but regional outages rarely happen. But every now and then, there might be issues that affect entire regions. It doesn't have to be the cloud provider. It can be from an ISP, for instance, that have issues with traffic towards a specific region. So these are some of the common weaknesses or potential weaknesses that we see in serverless applications that we can test for by using chaos experiments. So let's then look at some more practical experiments. So this is our simple architecture. It is a web service using an API in front of two Azure functions. One who retrieves or store data in Azure Blob Storage, one who retrieves or stores data in Cosmos DB. We also have some blob storage for the client to retrieve from as well. So things we can do then is we can inject errors into our code. So instead of our function returning a 200 response through the API to our client, we can return a 502, a 404, or something like that, to then test how does our application behave when those errors occur. We can remove downstream services to see how our application behaves or how our code handles these types of service issues. We can alter concurrency of functions so that it doesn't scale the way that perhaps we rely on it to do, to see how it handles those. We can restrict capacity of tables in our data store. Moving on, we can create different type of security policy errors, things that might happen through deployments or configuration changes and so on. We can create coarse configuration errors in our APIs. We can add different sort of service configuration errors to see how our application behaves then. And by using the disk space in our function, we can do things there. For instance, fill the disk space or remove the disk so that we don't have access to that as well. And then on to perhaps the mother of all serverless chaos experiments, the latency experiments. So we can add latency to our functions. And by adding latency, we're able to do quite a few things. For instance, we can simulate cold starts. That first time your function runs, or when it's scaling, when a new invocation of the function runs, to simulate those cold starts to see how it behaves. We can simulate, of course, cloud provider issues that might cause latency. We can simulate runtime or code issues, integration issues, but then, of course, also, as I mentioned earlier, test for our timeout values to make sure that they are correct and that they work as intended. So there are some tools we can use for doing chaos engineering on serverless. First off, we have a Gremlin, which is a SaaS solution commercially available. And a part of their system is called ALFI, Application Layer Fault Injection. Could be used for serverless functions, so far only for Java, but I hear they are about to release for Node, at least, I think. Then we have the open source Chaos Toolkit. And the Chaos Toolkit is not specifically for serverless either, but they have a system that's built around plugins or modules, and some of those are aimed at serverless services, so we can use that as well. Then we have the observability tool Tundra. They have added functionality in their tool to be able to inject failure into your Lambda invocations. So you're able to create different type of failure modes directly inside the observability tool Tundra. And then we have the NodeJS library called Failure-azurefunctions that I've created. It has some siblings as well, one called Failure Lambda and one called Failure Cloud Functions for the GCP users out there. And that is the tool we're going to use in our experiment today. So let's look at how it works. It's an NPM package for Node.js functions, available on GitHub. So please help contribute to that and create new failure modes. It's basically a wrapper for your Azure functions, where you wrap your handler and then are able to inject failure into it. And we configure it using Azure Vault. So we store a secret in Azure Vault, which contains the basically JSON with the configuration. So by updating that, we're able to enable, disable, and choose the different failure modes and so on. We have a few failure modes to choose from. Latency, of course. We can inject status code, meaning that instead of returning a 200, we can return a 404 or 502 and so on. We can throw an exception in the code. We can add disk space or add files to disk. And we have a deny list. And with the deny list, we're able to block network connections to, for instance, third parties or downstream services and so on, to be able to create experiments around that. So, and with that, we are at the demo part of this presentation. So to make it a bit easier to do these experiments to get started, I've created a simple site to easily show what happens, and we're going to use that. And as I said, we're using the Failure-azurefunctions package for this. The architecture for our demo is quite similar to the one we saw earlier. We have 3 functions in this case. And what happens is that on a regular basis, every 5 seconds, the front end calls an API which invokes a Lambda function, fetches data from Cosmos DB, returns that to the client, which then loads a new image on that site. So fairly basic. But with the help of that, we're able to then test some simple experiments. So with that in mind, this is the architecture. Now we need to create our experiments, of course. So we start off with those what ifs that I mentioned earlier. What if my function takes an extra 400 milliseconds for each invocation? What if my function returns an error code? What if I can't get data from Cosmos DB? So 3 different scenarios to create our experiments around. So the hypothesis is that if we inject failure to functions, then my application will use graceful degradation. So users of the app won't notice these issues. All right. So that brings us to the demo. Let's start off by looking. This is the site. As you can see, it's loading for each function. It's loading a new image every 5 seconds, hopefully. It's invoking, returning a 200 response, and fetching new images. So seems to be working right now. And as I said, this is stored in Azure Vault, the configuration. So for each function, I have a separate configuration, so I can inject different failures to them, enable, disable each and every one of them. The UI in Azure Vault is not my favorite, but I'm just going to show you how it looks. So this is the one for function 1, the current version, and it contains the secret value here, which is not that easy to see in the UI. But I promise you it's there. Right now, it's not enabled. What I'm going to do instead is use the CLI to inject failure. So this is the site. We're starting off with function 1. Here we go. So just using an AC command by setting a secret using it. And if we look here, there are several settings. The first one is enabled, right now set to false. So let's change that to true. The failure mode, as you can see, is now set to latency, which means that if we enable this, we will add latency to our function. We have a rate of 1, which means that we will inject failure on every invocation. We can set that to a lower number, which would then affect how big of an impact it would have on number of invocations. With the latency, we can set a minimum value, in this case 100 milliseconds, and a maximum latency of 400 milliseconds. So we'll use something in between there. There we go. So hopefully that should be enough. Let me just double check. There we go. All right, so looks like it was saved. And now looking at function 1, we can see that it's still responding with a 200, but instead of about 200 milliseconds, we are now at 408, 513, and so on. So we just added latency to each invocation. So far, so good. Our application can handle that we add between 100 and 400 milliseconds of latency to this function. That's good. So let's move on to the next one then. And now a bit of editing. This perhaps copy paste would be better, but not now. So the second one is called function 2, of course. And instead of failure mode latency, I want to use status code. Spelling status code, which means that instead of responding with 200, it will respond with the status code that I set. In this case, I'm using, this is the setting, status code 404. So it will return a 404 instead. I'm also going to change the rate for this to 0.5, meaning that it will inject failure on about half of the invocations. So not every invocation, but about half of them. All right, just double checking. Looks good, I think. I think it updated. Right. So looking at function 2, 200 first. $404. All right. So instead of getting a 200 with the reply of a URL for a new image, we're getting a 404. So the front end is not able to get a new URL to fetch a new image. So about half of the invocations returns to 200. We're getting a new image. About half is returning a 404 instead. So by doing this, we're able to test how does our front end handle these types of errors. So we can then start working with how to improve. We don't want users to see that there is an issue. Perhaps we can use graceful degradation, or we can count the number of errors in per minute, for instance, and find ways to resolve it in good ways based on that. All right, so that was function number 2. Now function number 3. And in this case, I want to do a deny list experiment. So changing back the rate to 1, changing the failure mode to deny list, and changing to function 3. Just double checking. There we go. Looks good. All right. And that is updated. Now let's see. So function number 3 should now not be able, there we go, should not be able to fetch data from Cosmos DB because the network connection is intercepted and blocked. So what we're getting is a 502 instead. So that's the response from, or the error that is thrown within our function. So this is also a good way then to test what happens if downstream services or third parties are unavailable. Once again, well, our application shows the error, which perhaps isn't good. We should have a way to handle that, either by using a fallback service, or we should do it by perhaps not showing that part of the UI. Right. So those were 3 different experiments we fairly easy can do using chaos engineering in serverless. So to recap this, I don't think I even said that, but everything fails all the time. This is a quote from Werner Vogels. Perhaps shouldn't be in an Azure presentation, but everything does fail all the time. And I think we need to remember that serverless in itself doesn't make your application resilient. It's the way we build our serverless application, the way we use services together, the way we use different features for error handling, and so on. And chaos engineering is there to help us find weaknesses and fixing those weaknesses. And it's about building confidence so that I can have confidence in my system, the way it behaves, but also in the people managing the system. And chaos engineering definitely isn't rocket science. I can do it, so you can also do it. And if you want more, there is a bunch of information. You should follow the Serverless Chaos Twitter bot that tweets a lot about chaos engineering. Look at the Serverless Chaos demo app. Look at the different packages. There's some videos and so on my site as well. And with that, are there any questions?
Thank you very much, Gunnar. That was a very thorough talk. You've already answered the main question that was asked in the chat, so we won't have to ask that one again. But I was just wondering, it seems like there's a big cultural component in chaos engineering. Do you find it easy to convince teams to care, or do people buy in quite easily?
I'd say that it definitely depends on the organization. Some organizations are really eager to use it, but some are not. And I think in some parts, the name is an issue for some organizations, because it really sounds like what we're doing is chaotic and that it's not that scientific as I'd like to say that it is. But we're seeing a greater adoption, definitely. And for instance, this was an Azure talk, but let's talk AWS for a while. Their well-architected framework now consists of several parts in the reliability pillar that is around chaos engineering. They more or less say that unless you're doing chaos engineering, you can't say that your application is reliable. So having these different cloud providers help drive these changes is important, I think. And Microsoft as well, they have great information about it in their documentation around chaos engineering and how to use it.
Oh, that's very cool. I'll definitely look into it more. You said that you've got to start with like finding out the what ifs, and then you can have your hypothesis and go from there. Yeah. Are there any like key important what ifs to start with if you were just implementing this on a team that hadn't got it before? Like, where would you start?
Well, I think, for instance, perhaps the easiest one to start with is the what ifs around third parties. So think about if we're using Twilio or we're using something connected to Slack or whatever third party it might be. What if that service isn't there? How does our application handle that? And in some cases, we see that people rely quite heavily on third parties. Well, it was just a day or two ago that there was quite a big disruption on the internet. And these things happen, and how does that affect us? So start asking the what ifs around certain dependencies that you have. I think that's a good way to start.
That's cool. We don't have any more questions, but again, thank you for talking. And if anyone watching would like to give a talk in the future, do reach out to us on meetup.com. Our planned next event is in 2 weeks, so hopefully we'll see you all then. Thanks, Gunnar.
Thank you.